Hello, everyone. I'm Susan Nash, AAPG, and it is just really a thrill to be able to launch into our third presentation in this webinar series that is from AAPG and GEODE. And GEODE is a DOE-funded endeavor that has the goal of making it possible to accelerate the use of oil and gas technologies for geothermal. And the overall goal is to help geothermal resources be developed. So this focus on our presentations is subsurface characterization. And John Holbrook has been involved in geothermal for a long time, so we're really thrilled to have him here. And I also want to just say a special thanks to Eugenia Torregosa, who is part of, she's a leader and part of Project InnerSpace and part of the GEODE project, and she has been really instrumental in this. And if she's here, I'd like her to say a few words. If she's not, that's okay too. I know she said she had to step away. At any rate, well, I don't see Eugenia Torregrosa, but I'd like to then just move over and invite John Holbrook to launch his presentation. So thank you.
Wonderful. Thank you, Susan. Well, first off, my name is John Holbrook, and this is my office. And I am a professor at Texas Christian University, and I'm a sedimentologist, and I want to talk a little bit about reservoirs and really get into kind of the intricacies of sedimentary reservoirs. And I'm going to begin by simply saying most of you will not use a lot of what I'm saying unless something really goes wrong. But it's a lot of things that we've learned about how sedimentary reservoirs are put together over the years, working particularly to try to understand really detailed heterogeneity and conductivity in petroleum systems that will be applicable to geothermal systems as well. So the title of my talk is, What are reservoirs made of? So let's start with something that we've been hearing all morning about geothermal. The way geothermal is generally going to work is you have some sort of a injector well and some sort of an extraction well, and you're pumping water through the rocks. Or alternative, you have a closed loop system, different ball game. You probably don't need me if you're doing a closed loop system. But if you're running it through the actual sediments from injector to extraction well, you really need to think about what's going on in the sediments in between, and what are the nature of that reservoir, and what can you expect in terms of pump rates and recovery. Okay, so what brings us here, of course, is instead of approaching this from the hot, dry rocks point of view where there is no existing permeability and you create it through fracturing, in this case, in sedimentary systems, we're starting with systems that actually have native permeability and the ability to move flow, and we may be enhancing it with fractures. So the enhancement of fractures, engineering thing, I'm going to talk more about native permeability and the whys and what fors. Okay, so where's the heat? One of the other things that brings us here is everybody has a sedimentary basin. They're all over the place across the United States. So we have a high potential, even at low enthalpy, to be able to produce geothermal in a lot of different places for a lot of municipalities. So it's got a widespread potential usage as we learn to crack this egg. And of course, in terms of the resource, as we've discussed a bit this morning, there's a lot of heat in sedimentary basins. It's not as much as in the hot, dry rock or in the mantle or frankly in the core, but it's a lot of heat that's in the sedimentary basins in the country, estimated as somewhere around 100,000 exajoules. So for perspective, the U.S. energy usage in the United States is about 100 exajoules. So there is a lot of heat down there, enough to make a difference. All right, so in sedimentary basins, the trick then is going to be to set up some sort of injector extraction system and run the flow between them and extract heat along the way. So that means you need to understand the intricacies of those sedimentary reservoirs you're pumping through if you want to make good predictions and have high probability of success. So what you need is a good plumber. That's what I do. We do plumbing. So the oil industry has hired us to do this sort of plumbing work for a long time. And there's a lot of amassed knowledge in how the plumbing of sedimentary systems work that have to do with detailed tertiary, primary recovery, secondary recovery, injection, extraction that we can use for geothermal. So tools of the trade, we have a lot of tools, subsurface, seismic, we have well logs, but heavily what we have is we have a priori knowledge. We have knowledge of the actual sediments themselves. Okay, I see a hand or two raised. Okay. Anyway, moving on, this is a typical petroleum workflow, and where we would start with our well log, our seismic, and our other data, and we move on through trying to develop a structural model. And as we move forward, we get to the place where you develop a sedimentary reservoir model. And so as we develop a sedimentary reservoir model, that's where we come in, is developing facies models and facies distributions and the stratigraphic model to move over towards a reservoir grid. Ultimately, all this is about lowering risk. Sorry about that.
Um, okay,
Yes,
so for some reason the slides are not advancing.
they're
So
not.
no. So why don't I go ahead and do the plan B then? Thank you, Cesar, for calling me. I just stepped away to the different room for a second.
Yeah, I saw some hands going up, and I was like, okay, I wonder what's going up. All right. So,
Okay.
okay. So just tell you advance.
Yeah, so unshare. So stop sharing.
Okay.
And okay, you need to stop sharing. So on the little green thing,
Yeah.
unshare.
Stop share. Got it.
So yeah, it should be red. Okay. So okay. So can you see it?
Sure can.
Okay.
So,
Okay.
so advance.
Okay, you want to just briefly highlight what you said a second ago?
Okay, where did it stop advancing at the beginning?
It never advanced at all.
Never advanced at all. Oh, okay. Um, all right then. So just briefly recapping a lot of what I said is, of course, we've heard this morning, simple geothermal model advance is where you have a advance is not advancing on my screen. There it goes. All right. Is you have an injector system, an extraction system, and you're pumping through a sedimentary reservoir. Advance. And of course, we're now pumping through sedimentary reservoirs, which have native porosity and permeability, unlike hot dry rocks, where we're generally in basement material, where we generally have to generate the permeability. So, advance. Okay. I'll tell you what, Susan. I'll just give you the signal. Can you see me?
Yes.
Okay, perfect. Um, so, uh, so we all have sedimentary basins. That's sort of the key there, is there's sedimentary basins all over the place. So even though the enthalpy of sedimentary systems is very low, we have a lot of it. So therefore, being able to tap all these sedimentary basins is going to be able to supply energy to a lot of places. So, up, advance. There we go. The other thing is there's going to be a lot of advance here, Susan. I have a lot of animations here. So, um,
Well, I can see your hand signal, so I'll just
okay,
hold
that'll
it.
work.
Yeah.
Okay, so one of the things about it, of course, is there's huge amounts of energy in the sedimentary basins. And we have about 100,000 exajoules of energy that have been identified down there in sedimentary basins. And we only use about 100 exajoules as a country anyway, so that's a lot of power. So as we move forward, then the real trick then with sedimentary basins is we end up trying to drill an injector, okay? Drill an injector, and then in between, you're trying to generate flow through sedimentary bodies, okay? So ultimately, we do plumbing. So plumbing is, the oil industry has been hiring people to do plumbing for a very long time, and there's a lot of things we've learned that's going to be very useful for applying to geothermal. We have lots of tools of the trade, lots of subsurface tools we have, but mostly what we have is we have a lot of models of how sedimentary systems work that we can bring to the table to understand what the intricacies of the sedimentary system look. So what we're seeing in our well logs, core, and seismic, we can understand what we're looking at and how those things are going to affect fluid flow. This is a typical petroleum workflow. And in that petroleum workflow, we usually start with seismic, well log data, anything we can get our hands on. We develop some sort of a structural model. And where I come in and all the sedimentology and reservoir people come in is when we start talking about the stratigraphic model and the facies distribution and distinction model. Advance. There you go. So that's our part, is developing the stratigraphic and the facies model to get at some sort of a reservoir grid as to what the permeability is going to be. Okay. And ultimately, this has all been about lowering risk. Okay. So we make a stratigraphic model and we develop those different ways using sequence stratigraphy has been very popular for that. But our model for how we're going to move water through the system depends a lot about the interpretations we make. And the same data could end up in very different reservoir models for distribution of sediments and porosity bodies. Ultimately, though, we end up with something that's rocks. And those rocks are unchanged by our interpretation. We're ultimately going to figure out how to move fluid through it. Okay, so most of the issues we have when we start talking about moving fluid through complex reservoirs is either about heterogeneity or connectivity. So heterogeneity refers to the variability within your reservoir. So one thing that we deal with a lot is reservoirs are very hierarchical. They are made of Legos, composed of Legos, building bigger things with bigger Legos, and at every level you're ending up with lots of surfaces that create heterogeneity. Can be flow baffles or flow barriers, but they can certainly change the nature of the flow. So internal reservoirs are complex. They have complex internal heterogeneity, as is typical. Okay. And when you see them in the outcrop, you see those mud drapes and all those little alternating facies characteristics that cause a lot of the reservoir complications that are going to impact fluid flow. The other thing is connectivity. So you may have a nice reservoir like that channel belt that you're going to try to send fluid flow through, and you've got a well on both ends of it, and you're just pumping through. But the other thing is connectivity. Those things are connected to other things by things that they incise and things that they impact. And reservoirs may be connected to each other, which you may or may not want, depending on the nature of the situation. Okay, so we spend a lot of time trying to predict this stuff. So one thing that's important is when you look at your actual reservoir, it may look like it's a fairly uniform thing, but it's not just a sand tank. The flow has to go around a lot of stuff and get caught up in stuff and move through lots of little surfaces and barriers that'll change it. Okay. So how important is that? Did your drill and your model turn out as planned? Well, the reality is a lot of this stuff won't be that important to you. If it's working, it's working. Usually where you're really trying to worry about this is when something goes wrong and you go, what gives? It should have worked. It should have been simple. Well, rocks are pretty complicated. So what I want to do now is spend a little time just talking about reservoirs and how they're built. And ideally, you won't use everything I'm going to talk about, but ideally what will happen is you'll have a better sense of how a reservoir is actually built to better understand the internal complexity of them, and therefore understand a little bit better how to deal with them and how to predict problems that you may have, or predict when you should probably be worried and when you shouldn't be worried about connectivity and heterogeneity in your reservoir. So let's talk a bit about how we build a sedimentary reservoir and what we've learned about the processes that go into building this reservoir so we can better understand how to treat that reservoir. Okay, so first off, let's start with a simple point. Let's just consider those ripples migrating along the floor, and they're going to migrate, and over about 20 to 60 minutes, they're going to migrate and build about 5 centimeters worth of sediment. That means if you let those things run continuously, in about 10,000, you're going to have about 900,000 meters of sediment after 1,000 years. Obviously, that's ridiculous. The radius of the Earth is only 6,400 kilometers. So clearly, we're not preserving constant deposition in the rock record. We're clearly not even preserving much deposition in the rock record. So for perspective, if you were to look at the Grand Canyon Paleozoic section and walk the Bright Angel Trail from the Tonto Rim up to the Kaibab Limestone and go through the whole Paleozoic section, and you considered continuous deposition and how much sediment you would make over that period of time, and then you realize how much sediment you've actually walked through, you would realize you'd only be preserving about 1/1000th of all the time that had passed as continuous sedimentation. So that's the rock record. Okay. Okay. So what that's led us to is a lot of criticisms of the rock record. Is the rock record seems to be pretty fractal. It's got some weird self-similarities, and also that signals in the rock record, things that we predict about sedimentation, oftentimes oh, there you go. Oftentimes are not actually things that are actually signals going into the sedimentary record, are not necessarily recording in the sedimentary record. And it's led to a lot of criticisms that just fundamentally said the sedimentary record really isn't recording anything. Here we go. There we go. So the stratigraphic record has been accused of being fundamentally unrepresentative of the geologic past, and there's no predictability at all from it. Well, that's a little harsh. There actually is quite a lot of predictability, but we have to take it into the context of understanding exactly how this thing works to understand what we're really actually preserving when we make a reservoir. So what do we do now? So let's consider this way. First off, I'm going to point out in this particular case that a lot of the stuff I'm going to talk about, we actually have a couple publications in our Science Review. You can actually go to them and you can actually read up on them on your own. And so you can read up on them on your own, and of course, largely we're talking about siliciclastics in this case, but much of this can be applied to carbonates as well. Okay, so patterns in modern versus ancient. Do we actually preserve? Okay. Do we actually preserve do we actually preserve what we see in the modern in the ancient? So the first thing to appreciate when you're looking at any sedimentary reservoir, whether it's carbonates, whether it's sediments, whether it's siliciclastics, what you're looking at is you're looking at a statistical sampling of the past, not a complete representation of the past. So everything we're looking at is a snapshot. So in these carbonates here of the Greenhorn Formation, these are preserving Milankovitch cycles. Each one of these beds is going to be a 20,000-year obliquity or something of that ilk. And each one of those beds is a snapshot, but it's recording a pretty good sized chunk of time. Whereas over here on these tidalites and these others, in these rather carbonaceous sands over here in the Pennsylvanian section, these are tidalites. They're actually preserving individual laminations from daily tidal cycles. So your snapshots are not equal, but what you are getting in each case is these are preserving some sampling of the past, not a complete representation of the past. Clearly, you can't preserve every day that ever passed as tidalites in the past, but you're getting some piece of that, and that's what's showing up in the rock record. Some spatial temporal sample of something that went on there and got stashed in the rock record, and that's what's making our beds. Next slide. Okay, so here's some guidelines we can work with in terms of interpreting the sedimentary rock record. First off, guideline. Stray to preserve the characteristics indicative of the depositional environments, because that's all they can sample. So, in short, you can only preserve statistical samples of things that were actually happening there. So you don't randomly preserve any kind of sedimentary sample. You have a delta that makes a certain set of sedimentary samples. Those are the deposits you're sampling from to make your deposit. And only the ones that would show up in that environment are actually the ones that are going to preserve at that location. But not every sedimentary deposit that's been formed will show up. Okay, so this is an example of a point bar. As it's built, you're creating a very heterogeneous reservoir. It's got mud drapes, it's got sand drapes, and they alternate with each other. In this particular case, they're coming from specific accretion events as the bar grew. And eventually, it's making a bar with a distinguishable shape. Okay, that's made up of a collection of these samples. So that's okay. Go ahead. The good news of it is, since sampling is not random, you're actually sampling from the environments there in some proportion of the generation of sediments that are happening in that environment. It means you're preserving things that are actually representative of the environment of deposition at the time. So good news, uniformitarianism actually works. Okay. Despite these really low sampling rates of sediment into the rock record. Okay, so reservoir analysis actually then about understanding probability of spatial temporal statistics. We are preserving in our reservoir some sampling of the history of things that were happening at the same time in some very small amount. And all of these little small scale reservoir units are accumulations of these things to build a bigger unit. So the rock record is the statistical sampling machine, not the tape recorder. Okay. Next slide. This is some work that Zane Job did here, and so he's pointed this out. Straight are records of the past, but not complete records of the past. So in this case of this deep sea alluvial fan, submarine fan, what's happening is you're depositing turbidites. By the time you get out some of these distal turbidites towards the alluvial plain, you're only preserving a turbidite about every 100,000 years. So a turbidite might have happened in a week, and it might be about 20 centimeters thick. and you're only preserving, but you're not recording them constantly. You're only picking one of those up about every 100,000 years. Closer in on the fan, you might get a better sampling. It might be preserving one every 1,000 years, but that's kind of the way it works. So not much. So next slide. So ultimately, that's why that we get why that the rock record looks so incomplete and we're preserving so little sedimentation. The reality is sedimentation isn't happening very often, and we're not actually recording it. We're actually not recording all of it. So you're getting some samples of the ones that happened. Next slide. Most of the time recorded is in the surfaces between the sediments then. And so the short answer is most of the time in the sedimentary record, nothing is happening. There is no sedimentation. We're getting random small sedimentation events, and we're preserving some small fraction of those. And that's what we end up with is that sample set that's making up our reservoirs. Okay, next slide. Okay, there we go. So now hierarchy. This is something that we have to deal with when we understand reservoirs. What do I mean by that? Is actually in any given sedimentary body, regardless of whether it's a carbonate reef, it's a river system, it's alluvial fan, in all cases, what you find in a reservoir is it's a bunch of smaller pieces snap together into bigger pieces, snap together into bigger pieces, making bigger pieces. So you have orders of hierarchy of sedimentary reservoir bodies. You may be dealing with small scale ones that represent small scale ones or higher order ones. It depends on the nature of your reservoir. So for instance, just as an example, if you're pumping a flow through the whole Wilcox, and through valleys or something, you might be working at a high level architectural scale made up of channel bars that have made channel belts that have, pardon me, the automatic light thing that's decided I'm not here. But you might start out with cross sets that made bars, that made bigger bars, that made channel belts, that eventually filled valleys, that eventually made these big valley sheet complexes. And you might be working at that large scale. But on the same token, when they're working up here in Alberta in the oil sands, most of the time they're looking at individual point bars. They're just huge. Those are their reservoirs. Totally different hierarchical scales where your reservoir applies. But what's important is no matter what scale you're working in, you're building that thing from smaller pieces. And the complexities of all those pieces are part of your problem as a reservoir now. Next slide. So each order in hierarchy elements then is an amalgam of the elements sampled from lower orders. Next slide. So a change in sampling at one order of that hierarchy will manifest across multiple orders. So ultimately, what's happened is the reason you might see, hey, that looks like a meandering stream deposit versus that one looks like a braided stream deposit, is because somewhere along the line, at some order, you've changed the nature of how sediments were sampled. So instead of sampling sediments on the face of some big point bar, you're now sampling them on mid-channel bars. And so now you're actually showing up with a braided river now instead of a meandering river. So little subtle changes along the way at any level of the hierarchy are what determine what your ultimate larger reservoirs, how it's going to be built. Next slide. Okay, the other thing is this is one of those obvious points. Rates for any process at any order higher are limited by the law of limited durations. In short, slide. No part of a process can take longer than the process. So the things that are actually happening at the lower orders, they can't take longer than the things that are making the higher orders. So for instance, if I'm making cross sets and those cross sets are making bars. Well, the cross sets can't take longer to make than the bar does because the bar is made of the cross sets. Then the bars are making up channel belts. Well, I can't actually take longer making a bar than to make the channel belt. And similar up to the channels make larger channel belts, which make large amalgamated complexes of channel belts that would be something that would be more akin to your flow unit. So, next slide. So if you're trying to interpret your sedimentary body and say, what made this reservoir? What things forced it to be what it is? You have to be thinking in terms of the rates it takes to make a sedimentary body, and then say, well, what things would actually work at that scale? In other words, if I'm looking and saying, climate change is causing me to get a big sheet of sand that I didn't have before. Well, okay. Climate change, sheets form on scale of sand form on scales of millions of years. A 10,000-year climate change doesn't do that. A 10,000-year climate change changes an individual belt inside that reservoir, which works at that scale. Also, then go ahead, Susan. Also, completeness across stratigraphic hierarchies, it isn't just determined by how much you're preserving and sampling from your sediments. It's also determined by how much of that actually survives to make the sedimentary record. So just because you manage to store some sediments in a natural physical environment doesn't mean it's actually going to make the break to the rock record, because things happen to it along the way afterwards. So this is a story that Paul Durkin did. He looked at meandering rivers and started looking at the individual pieces, and he looked at different scales. Okay. And he started breaking it up into depositional pieces and said, what are the odds you're going to preserve any given piece? So rivers are great for this because you can actually see this happening in real time. Next slide. And what he determined is simple. When you looked at pieces of bars, and whole channel belts. Next slide. And compared them, you found the odds of one of those getting destroyed before they made the rock record followed a logarithmic curve. So most of the deposits you actually are preserving are getting destroyed before they're even getting into the rock record. So only some small portion of the stuff that was that small portion you preserved is actually even making it into the rocks to begin with. So so the point is, you get a picture of it when you think about how you preserve rocks. The first thing to realize, you may be making a lot of sediments that you're looking at in this modern environment, but what is happening is most of those sediments are not getting deposited or getting destroyed long before they ever make the rock record. And you're only preserving some small sample of all those things that were actually produced, all amalgamated together into little pieces that are all gelled together into one larger thing, and then those things into larger things, and those things into larger things. And yeah, now that kind of gives you a feel for what you're dealing with when you're working through flow, and why the petroleum companies spent so long trying to get a handle on all these things. All of these different layers are their own little reservoir units. You're snapping together to make a bigger reservoir unit. So reservoir units end up being complicated. Next slide. Okay, next slide. Okay, so the other thing that we run into is stratigraphic record bears some fractal characteristics. So this is the math people talking. In other words, all those pieces of pieces of pieces that build up a reservoir. If I take this reservoir at the bottom here, functionally it's a sheet sandstone, but I start breaking it down into pieces, well, then I find the little pieces look a lot like the bigger pieces, and the smaller pieces look a lot like the ones before. And if I keep breaking it down into smaller and smaller reservoir elements, I find the smaller elements look a lot like the bigger elements. Okay. Where that comes into trouble in a real interpretation is here, and this is one of the most common mistakes in reservoir interpretation. You see a shape, and that shape is familiar. Well, the reality is, since the rock record is hierarchical, it's made of pieces that make up bigger pieces that make up bigger pieces. Well, since those pieces quite often look alike, you can mistake the scale you're working at. You can look at something that looks familiar and forget something much bigger would look the same. So I'll call your attention to these two sequences down here in the lower left. The bottom one, back up one if you don't mind, Susan. The bottom one is a bunch of large-scale composite sequences of the entire Brazilian shelf. So you're talking about the entire Miocene depositing those 3 units. Look up above at the sequence right above it, and you'll see the, which I colored the same just for effect, but note how similar that particular sequence looks. That sequence, however, was made in, that's 2 sequences made in less than 1,000 years on the Dead Sea, and represents tens of meters, not hundreds of meters. But yet, geometrically, they look alike. That's because of this fractal effect. Where we run into it the most is when you're working in things that involve channels, and you'll like deep sea fans or fluvial systems or some any kind of flow system. You'll see a full-born valley has a shape a lot like a channel, which is a lot like an individual scour within the channel. And you'll find there's, for instance, in a fluvial system, what you'll find is there are things that look like channels. There's 6 different orders of that hierarchy that all look like channels. And if you're just seeing channels, you could be looking at valleys, belts, or channels. All of them kind of look the same geometrically. So your challenge often in interpreting the reservoir is figuring out where in that hierarchy you are and which one of those reservoirs you're looking at, simply so you can make better predictions about their behavior. Okay, this is another one, is when you think about whether a section of rock is complete. Well, it really depends on what you're defining as complete. So, for example, we're over here in the Castlegate Desert, we're down here in the Blackhawk section. In the Book Cliffs, if you're looking at sequences, next section, if I say I'm defining a section of an individual sequence as complete, by definition, it's complete. But if you break it down and say, how complete is it when I start thinking about the individual sand sheets within it? Well, now that's only, you're looking at about 1/10 of all the time that's passed is preserved, and the rest of it is the bedding surfaces between. If you break those down into those sheets into the smaller sheets, you'll realize you're only looking about 1/100th of the time that's passed. So completeness ends up being in the eye of the beholder. Whatever you decided was a complete section by definition is. But let's take it the other way. Here's something a little more practical to think about, is that if you consider an individual bed of rock, just an individual layer of rock, carbonate, siliciclastic, whatever, it doesn't matter what it is, and say, that bed, by definition, records continuous deposition. It is complete. And you take it from that point and go moving up the section to the architectural elements. Those are the base reservoir units. Then you bring them up from there. All those reservoir units make up what we call a sequence. So between one continuous sequence of deposition between unconformities. Well, if you actually look at how much time is lost typically, okay, then you realize that if a bed is complete, what we call a conformal sequence is only recording 1/1,000,000th of all the time that's passed. So that's typical. So what we usually say complete That's a complete section. It doesn't have any major unconformities. If you think about your typical complete sequence of rock without major unconformities, reality of it is in terms of continuous deposition, how much rock are you looking at? How much of that rock is recording actual deposition? Yeah, it's about a millionth of all the time that's passed. Okay, which brings us this thing called the Sadler effect, which if you're trying to interpret reservoirs is a very practical thing, is when you start looking at sections of rock, the thicker the section of rock that you look at, the longer duration that seems to have passed. So if I look at a really thick section of rock, it might record several million years. But if I look at a really thin section of rock, say I look at 10 meters of rock, I might look and say that records 2 million years of time passing. But if I look at individual layers within it, say there's a few beds, those beds might only record a few tens of thousands of years, or an individual layer might only record an afternoon. So the shorter section I measure, the less time that's passed, and it's not linear. And that's simply because the more section you're incorporating, the more of these longer status surfaces where nothing is happening that you're incorporating. Okay. So, so when you're trying to interpret rocks, the main thing we usually do is we try to project the modern into the ancient. So how do we do that? We do that by a couple techniques. The main tool that we use is we look for modern analogs. We simply look and see what sorts of modern systems preserve the kind of deposits we're looking at in the ancient. Well, that means what we're remember. First thing we have to remember is what we said before is that is that the rocks are actually recording just samples grabbed from that environment and stashed in the rocks, and some very small proportion of all the deposits, and each of the deposits from those there had long statuses in between. So you're only grabbing a few samples from that depositional environment to generate the rocks you're seeing. So why does that even work? Well, first off, one reason it works is because even though you might only have a few samples that you're grabbing, a lot of them are very distinctive. So we use the concept of indicators. So we might not have grabbed many samples, but some of those samples may be very, very distinctive of, say, a carbonate reef. So let's consider this. Here's just some snapshots of one place I've worked. Let's try to figure out where this is. So it's just some samples of some snapshots of some moments. Well, of all these samples, most of these aren't so useful. Okay. There we go. So some of these are what we call poor indicators. It's a rock. It's some buildings in the fog. It's a dune. It could be any place or anything. Lots of things that we sample in the rock record, like a cross set or some ripples or something, they can form so many places they don't tell us much. But what we do is we look at some of the other samples that have been collected and we realize, here we go, these are better. We know we're probably somewhere in the Middle East when we start seeing these. And then these are pretty darn good. That's the Sphinx. That's an Egyptian tag. I'm in Cairo, or I'm in the broader delta and so of Egypt. So the thing is that's how we usually approach the sedimentary record. Some things like I found in echinoderm, it's got to be marine. Even though we only have one sample of it, it's that sample, you had to have had an environment where that sample could have been taken for it to be there. And that's how we interpret rocks. We don't have to have samples of everything. A sample of something that could only have been in a certain place will help us interpret things. The other approach that we often take is we'll look at these spatial temporal samples and we'll go, we'll look at them and say, those are useful, they tell us things. The other way that we will approach it, okay? The other way we'll approach it is by the law of large numbers. We'll just simply say if I take enough samples of things, they will converge on some average that will help us. So I'll go out and take a bunch of porosity samples out of these rocks, and even though I might not necessarily understand each one of them, exactly what's going on there, I know if I get enough of them that I will get some convergence on an average for this thing. So an example of that in the rock record is we'll take paleocurrents. These dunes are moving all over the place, and they're moving. Some of them are moving downstream, some of them are moving obliquely, they're all wrapping around bars and bar faces, and so the dunes are piling up as elements making bigger things that are the bars in the channel. And so ultimately what's going to happen is I can look at all of those things and I can say, even though I don't have to know what individual ones are, I know if I take enough cross-set orientations off those bars, I will come up with an average that says downstream, even though individually they're going all over the place. Okay. So the other thing we have to do is when we look at modern systems and make that analogy, we have to extrapolate them into deep time. So typically what we're having to do is we're having to think, how would that particular thing preserve in deep time? The good news of how that actually works is that every time we take some sort of a sampling of something and stash it in a modern environment, that sample is equally valid as a sample, whether it happened yesterday or it happened in the Cambrian. If I'm preserving a set of cross-sets on the face of a delta, there's no time difference between a set of cross-sets in the modern and the one I preserved in the Cambrian. It's not like when I look in deep time, processes slow down. They don't. You were only preserving some fraction of all the things that happened in a modern system to begin with. So I make a delta. Well, a Cambrian delta looks like a modern delta, or more I'd say like a Pennsylvanian delta looks like a modern delta. Why? Because if you made them the same way, they're only sampling a small piece of time. The delta you have in the Pennsylvanian would have preserved the same way as the one in the modern, just preserving some fraction of all the time, a fraction of all the deposits that passed. But each would be equally valid. So that's why the rock record works. That's why you can use modern analogs. You're not preserving time differently in the ancient than you are today. Okay. Next slide, please. Okay, next slide. Okay, this is a concept I'm going to introduce that is kind of that it's autogenic versus allogenic. This is something that's kind of stratigrapher talk, but they actually boil down to something relatively simple. Next slide, please. An autocyclic or allocyclic process are the intrinsic natural things that every depositional environment does. So, and whereas allocyclic processes are the things that control it from the outside. So, next slide. So, for instance, allogenic processes are things that change the energy or matter into the system externally. So there are things like sea level change, lake level change, tectonics, things that force the system. Whereas autogenic things are the things that actually are making the sedimentary deposit. So the actual reservoir elements we're seeing are being made by the autogenic processes. Things like migration of a point bar. Whereas the allogenic things are more like sea level rise, sea level fall. So here's the gist of it is all your stratigraphy are being made by the autogenic processes. Allogenic processes don't generate any stratigraphy. They are just influencing the way that these autogenic processes are working. So things like I built a bar. I have catch up and keep up in a reef building a packet. I have a beach prograding forward. These are autocyclic processes. Nothing has to change for those things to take place. They just happen naturally. They build all the stratigraphy. The allogenic processes just influence how those things operate. So, in short, allogenic depositional processes don't exist. It's all autogenic processes, natural intrinsic process to the system that are building all of our stratigraphy. And allogenic changes only show up in the way that they're actually altering the autogenic processes. Next slide. So the good news of it is, though, is in terms of all the things that can influence deposition, there aren't many of them. And we've learned what they are, and they repeat through history. We've got sea level change. We've got tectonics. We've got climate change. We've got some things we've learned about within them. But for the most part, what happens is most of the things that are actually causing patterns in our stratigraphy that cause reservoirs to change and give us the ability to correlate happen repeatedly throughout time. And not a lot of that changes. So you can do something like sequence stratigraphy that tracks sea level changes and looks at the surfaces that they make simply because a sea level change in the Quaternary is not that different than one from the Pennsylvanian, and it's been that same process has been happening, over and over again through time. So again, that's how we interpret the rock record. We look for changes that we recognize and see, and we understand in the modern, and we look for them in the past. Okay. So, in terms of whether an event is going to cause us to make a stratigraphic reservoir, first off, it's got to be big enough. So not everything that happened in the past is going to preserve. So for instance, this is just a little experiment pointing something out, but if you have your channels pouring down a tectonic basin and you create subsidence, you might see the rivers clustering towards the low spot. But if there's actually a powerful enough sedimentation rate in that basin, that little tectonic sag will not be able to register. So not all things that have happened tectonically, sea level, whatever, will necessarily register in the sediment. They have to be big enough to alter the system in some way to actually be able to show up as a signal and to actually generate actually change the nature of your reservoir at all. Once in a while they do, though. Okay. Okay. Now, one thing that we notice is that if you have a system where we talk about autogenic processes like sea level change and things like this, changing the system, we generally say they're regional. Well, the thing is, if something is regional, like I made a major sequence boundary that I can track over states, that is a real external change to the system. It's something you can correlate. It's real. If it's regional and it's big, it probably is and you can track it. It probably is because of some major change in the rock record, like a sea level change or a tectonic change or a change in basin subsidence or a change in climate or something that affected everywhere all at once. Next slide. The opposite is not true. You can have local tectonic changes, local climate changes and stuff that affect an area right there and nowhere else. So this is just a little look at the New Madrid seismic zone in the Mississippi River. But sure enough, the patterns of sinuosity have changed. You can keep hacking at that, have changed considerably over time as a result of individual earthquakes. This is just affecting here. It isn't affecting the whole state of Missouri. So things that are external changes to the system can happen just right there and happen just a local place. But when you do see things regional, it probably is you're probably looking at a change that is something big. Okay. For the sake of time, I'm going to call it right there, Susan.
Okay. So we'll have time for questions. You want to just move over to questions?
Sure, please.
Okay. So if we look at the, well, okay, there are a lot of, you might look through, scroll through some of the questions in the chat and see if any of them really appeal to you or jump out at you. In the meantime, I'm going to continue clicking through your PowerPoint because I think I'm curious.
Okay, so where are we at here?
I think
Where are we
that
going to
one question that comes to mind that you might talk about, and I'll stop sharing to make it less distracting. Whoops, I'll make it. So you might talk about the importance of all of this the in the whole issue of geothermal and geothermal reservoirs. Like how does it really matter?
And of course, that gets down to a place where I started with. A lot of this stuff you'll brush over, and you might get lucky. Because what I'm really getting at is when you build a sedimentary reservoir, you're building pieces. You are building it from pieces that have been preserved preserved over time, building these little blocks, which build bigger blocks, which build bigger blocks. Each one of those levels is a potential source of heterogeneity. And when you start constructing flow models through your system, those things will be there. You can ignore them, but they don't ignore you. They do exist. You might get by with not worrying about them because the system overall is still behaving sufficiently uniformly to where that these things won't matter. On the other hand, though, what's more the case is when you're actually talking injectors and extractions, sometimes the water doesn't go where it's supposed to go, or things don't connect up the way that they're supposed to. That's when you start thinking about, okay, how is this reservoir made? What are the pieces? Because if I'm going to inject into one place and extract from another place, that means that those two things need to be connected by some path that's actually going to be useful for me. So with geothermal reservoirs, it's going to end up being the same as we do with petroleum reservoirs. You have to get those things to connect. And if you're in a complicated reservoir with all of these little pieces and you didn't match piece to piece and you don't get a connection, your flow's not going to actually connect from your injector to your extractor. And so they've been dealing with this with petroleum for a very long time. These different intricacies in how the reservoir is made, it actually determines whether injectors and extractors actually match up or they don't. So where you deal with this with geothermal is you have to understand enough about the reservoir just to know what my probabilities are that the two things I've drilled into are actually going to connect up and they're going to pump through the way that I expect them to do. And if it's not a complicated reservoir, you have less problems, you have less, but as you get deeper into, but all of these complexity I'm talking about are in there whether they're causing heterogeneities or not. So we spend a lot of time trying to understand how reservoirs put together, not so much when things go wrong, right, but when they go wrong and things don't actually connect. You have to ask why. And so in all of these complications of hierarchy and connectivity, that's where the problems are going to arise. So the first place you usually go with geothermal, especially here while we're in the earlier stages, you go for the simplest scenarios possible.
Yeah, that makes sense. Okay, so looking at some of the questions. So Harold Buitrago says, by following a classic oil and gas workflow, one can observe that the rock is characterized in detail in terms of properties such as porosity, permeability, saturation, layer geometry, facies, etc. But temperature is not estimated with the same level of detail even when the project is aimed at geothermal energy? Is temperature not as important as the other parameters?
And that's a good point, is that temperature has heterogeneity too. Um, I would also say that part of it is not my strength. I know a little bit about it, as a lot of people do, but there's people on this going to be on this course would probably be better at that question than me. But one of the big problems with this is you both, as you say, you've got two moving parts here. You've got temperature resource and you've got fluid. So one of the things about the temperature is, at least, we do have some sense that the rocks are generally heated up close to each other at some depth. There is different thermal capacity of the rocks, but that difference isn't the really huge one. The really big problem you're running into is when you start running flow through, you are depleting heat along the flow paths. So the heat has to come in and replace that heat. So where a lot of the problems with the permeability and the flow end up being a more intricate problem is that the way you're actually running the fluid through the sediments is determining where you're actually mining the heat and where you're actually lowering the temperature of the reservoir. So you might be in a situation where it's not so much a matter of the base heat initially being that uneven, it's that after you turn on the pumps, you're going to make it uneven. You're going to start extracting heat more from certain areas than others. So knowing how you want to run your flow paths has a lot to do with how you're going to ultimately generate the heat structure. And I think the bigger question in all that is more a matter of, you have a recharge problem over time. How long does it take to recharge this heat after you've extracted it? And how long can you extract it before that your heat source is depleted? And so that's where flow paths often come in, is the way you've designed your flow paths, and the more dispersed you can get, the broader heat structure you're actually draining.
That's really interesting. And that kind of leads to an interesting diagenesis question. So Rex comment asks, John, how about precipitation or originating from carbonate sedimentary rocks? When specific geothermal wells are producing initially, but then they deteriorate through time due to calcite, silica, et cetera, blockages.
Now, one of the things I didn't bring up before is one of the reasons what got me into geothermal is I ran SED HEAT, which was the National Science Foundation's research consortia on sedimentary geothermal back starting around 2010. And so back when this wasn't what everybody was into, we were looking at this. And one of the things that came out of this that we all understood was one of the biggest problems we face when you turn the pumps on and you start flowing hot water through these systems. Diagenetic processes speed up, because normally hot water would not be flowing that fast through these rocks. So I think the answer to that is we've got a lot to learn yet about, as we launch deeper into this geothermal world, about how diagenesis fouls up a system with time, and how much, and how you get around it. The main thing I would say about this one is I don't have an answer to this. I would say that all of us sitting around looking at it we know this is a problem. And we know it's something we're going to have to learn more about, because we know it's going to happen, that you will actually start moving precipitates in that water, and it will reprecipitate and clog up reservoirs and block flow paths that you were dependent on before. What we don't know is just how bad of a problem that's going to be.
That's so true. Okay, so Lena Broadley says, thanks, John. Really liked your analogy for interpreting from snapshots. Fun way to demonstrate it. Another person also pointed out that seeing the camel was like seeing a trace fossil. But anyway,
Yeah.
I thought it was cool too. But and then we add to that the fact that we all we have is log data from 8 inches or 6-inch boreholes So we can't even see what's preserved. Geologists are detectives.
No, and 100%. Matter of fact, the irony I'll take that analogy a little bit further. It's like one of my students did the subsurface of the Raton Basin, and initially that was brought about because Pioneer had geothermal interests there. And we spent a bunch of time analyzing the Raton Basin, looking at these little well logs and doing all that sort of work. And after he finished, he went on to be a detective. So if you get in trouble in Denver, you will meet my student, Sean Horn. He's a detective. He's a narc there.
How fun.
Yeah. But
Amazing.
it's a very similar thought process.
Yeah, definitely. Definitely. It's fact-based and analysis, and I mean just really having to untangle cognitive bias too and identify yourself, your own cognitive bias. Okay, so David Weinberg says, I particularly like your hierarchy and fractal discussion, but the fact that specifics geometry seem to be similar despite a position in hierarchy doesn't really come as a surprise. Except for dealing with quantum scale, the sedimentary physics of the Cambrian are no different than the sedimentary physics of today. For instance, the physics of a fluid acting on a grain, think Hillstrom, is the same, although absolute values may be wildly different, silt grain versus cobble.
Well, and what I would say is you're way ahead of the curve because it's taken us a long time to really appreciate that point. Physics doesn't change. You're making the same kind of samples and storing the rock record in the Cambrian and the Paleozoic and the Mesozoic as you are today in much the similar ways. What's different is our natural mind tends to go to the place of that's ancient and that represents a long time. So it must, and I've looked at the dates, and this is 1,000,000 years of deposition. Whereas I'm looking at Quaternary and I'm like, oh, that's 10,000 years of deposition. It's the same thickness. Processes must be different in the past. They're not. That they really all operate pretty much the same. So that concept that I'm looking at a bed in the Cambrian and I'm looking at the physics of how it was deposited is the same as today. It's a simple concept. It should be an obvious one, but it's not the way we think. Matter of fact, I will also point out my colleagues over at Cambridge, Neil Davies. He just wrote a review paper on paleontology explaining why fossilization works on that point. Big review paper simply because he said, you know what, a Cambrian fossil, it's preserving fossils just the way as you would today because the rocks are working the same way as today. But the point is that Cambrian sample is just as valid of a sample of the Cambrian as a Quaternary sample would be today. They're not different. Then the other point that's made that's very important too is it's not surprising at all that rocks have self-similarity up the hierarchy, and something down here at this lower level looks like something that's higher level. But what I would also say is the easiest consulting money I usually make is when I walk in and we're looking at a bunch of seismic data where you're just seeing geometries, and you'll say, you're not looking at a channel, you're looking at a valley. They look the same on the seismic, but in terms of the geometry, but they're completely different scales. The problem is that when you start trying to interpret it, the way you would actually go about making a fluid flow model through a valley system is different than the way you would make it through a channel belt. So even though they looked the same, the way you would handle them would be different. You'd be thinking different scales and different processes, but that fractal effect gets us every time. It's like I say, you're looking at seismic, you see geometries. Your first task is to figure out where in that whole hierarchy are you really at before you move forward with your interpretation. And it's not, and if you're not aware of this problem, you can make some big mistakes. And even if you are aware of this problem, it's darn hard not to make these mistakes.
Yeah, that's a good point. And I don't know if you in the audience were here for Eric's first kickoff presentation, but he posted in the chat And so, but Eric, if you're here, if you want to, you can make your comment in person, turn on your camera and mic.
Hey,
Great.
thanks. Yeah, I was stuck on mute there for a bit. I was just going to say, diagenesis is going to be variable depending on temperature, pressure, and the fluid geochemistry in these different aquifers. And even like on the Gulf Coast where I'm working, the fluid geochemistry in the Paleogene Wilcox Formation is quite different than the water geochemistry in, a carbonate formation just, 10 or 15 miles away. So it's going to depend on depth and all these different things.
That makes sense. So we have a few more, couple of more. Let's see. Oh, there's a request to send the slide deck for John to all the registrants, and I would say that be careful what you ask for. It's 60 megabytes. Is all the animations and things. In fact, I think that may have been why it was kind of sticking a little bit for me and why it was sticking for you. Because it's
Too big.
yeah, it's a nice, and it probably works fine if in a regular situation with a presentation, but when we put it in Zoom and complicate it, then there's just too much going on.
Yeah, this isn't the first time I've done that to you. Yeah, no. Okay.
Yeah, we have some really wily gremlins that really know how to come out of hiding.
We do.
Great. Okay, so let's see if we've got any more. Let's see. Yeah, I think this is pretty much everything for the questions. So any final thoughts?
Well, final thoughts. What I would say is appreciate that in the petroleum industry, there was a lot of money involved. And primary, tertiary, secondary recovery, we had a lot of impetus to really get down and learn the nitty gritties of how a reservoir is put together. And there was a cycle in the petroleum industry where it was like, hey, it's an anticline. I saw a fault, drill a hole, and a lot of times it worked because this was early in the game and you were going for the easy stuff. What happens over time is that you have to start thinking about recovery on the scale of we've got some complicated reservoirs and we have to figure out how to get the oil out of through all these little baffles and everything. And well, that's why people like me did a lot of this work, is to understand what all those complicated baffles and barriers actually were and why they were there and how the rocks were put together. In a lot of the early developing geothermal, it's like, we're not ready to take those risks. You're looking for the simplest reservoirs you can find and saying, it looks relatively uniform and I can drill here, I can drill there, or I'm just going to bypass it and do a closed loop because I don't want to deal with the complexities in the reservoir. And right now we're at a phase in early geothermal where a sedimentary geothermal to where we can't afford those sorts of risks just yet. This needs to work, and you want to hit things that you think have a good opportunity of working. But as this thing matures and we get deeper into geothermal, we start trying to do more and more places where the situations are more complicated, we're going to go the same path that oil and gas went, where that we need to understand these intricacies a lot better in order to understand better how we can say, if I can hit this here and I can hit this there, I can get these to connect and get the flow rates that I want, even though now I'm having to accept those intricacies and complexities in that simple reservoir were always there. It's just they weren't causing me problems. Now they're causing me problems, but I still need to figure out how to produce this. Well, It may be that you realize I just need to frack the living daylights out of it to get around this. You might decide I want to do a closed loop. You might decide a lot of things. But the point is as we mature in this science and get better at this, we're going to care more and more about these sorts of intricacies of the reservoir and the problems that you potentially are going to run into with geothermal, just like we did with oil and gas. So it's just, we haven't quite got there yet. But the good news for geothermal, a lot of that legwork's been done.
Right. And you know, the thing that's the big game changer for all of us is that we've got these enhanced geothermal systems. So we're using oil and gas technologies for hydraulic fracturing, et cetera, and the equipment's there and people have a lot of experience. And then the second big game changer is focusing on sedimentary, so that it opens it up for for utilization if we can get over some of the technology issues, like the massive amount of water that's required, or some of the lower temperatures, the inefficient binary systems, et cetera.
Yes. And of course, that's one of the things I would say. Again, like I say, from my history running said heat, when we started out in about 2010, talking about sedimentary geothermal, again, there were lots of people who were playing with this idea. The role there was just to get everybody together there in the same room to talk about it and see what we could do to improve on it. And it was good. We laid a lot of groundwork that's now being actually utilized. At the time, it wasn't really very economical, though it wasn't a single geothermal major play in Texas. But what was the problem at the time is the expense of this was very high, and the cost of actually producing electricity was high, and getting from the low enthalpy that you usually run into in sedimentary basins was unlikely. But a lot of what happened along the way was really improvements in this binary technology to where you could actually start extracting heat from these low enthalpy systems. And then guess the word I used to say is, over that time of span, when it came to generating kilowatts of power from sedimentary geothermal, we went to maybe from dollars to certainly for pennies. The technology has gotten a lot better in the last couple decades. There's one thing else that I would like to say in closing is much of this discussion has been about primary production of geothermal. Well, you drill a hole, pump in between, extract the heat. And what are we going to have to do about all those sedimentary pathways in between? And do we want them dispersed, or do we want them direct, or how are we going to handle all that heterogeneity? Well, okay, so a lot of my discussion was about why is it heterogeneous? What is that sedimentary reservoir? Well, there's another way to look at it is that, of course, SAGE has gotten into and so forth, and it's a very good thing, because all this time we spent looking at sedimentary geothermal, one of my big takeaways was where the real game changer future in sedimentary geothermal isn't maybe so much in extraction of heat as it is in storage of heat.
Mm-hmm.
Because one of the things we walked away with all this discussion is one frustration of sedimentary reservoirs is they're all just at the floor of probability in terms of heat, in terms of the amount of heat that's available in that reservoir. It's just almost enough to be highly profitable. But another way to look at it is that's what we call a base charge in a battery. It's already, you don't have to heat the aquifer up. It's already about where you want it. You can use that and heat it up a little bit to get it into economic levels from solar power that you otherwise would have put to waste. And coupling geothermal and solar systems as a way of generating a little bit of heat and then storing that heat in the ground and running your geothermal for your base load, that's going to be probably where we figured out that was where probably the future is going to be, where anybody anywhere could be using geothermal as a primary source. They're really using the solar as the primary source. They're just using the solar to keep the heat up to economics in the geothermal system. And like I say, I think that's where our frontier is. If you really want to talk about powering cities anywhere, it's going to be spiking the heat in those reservoirs just enough to where that you can make them economical using the solar and using that feedback loop.
That's really interesting. And that's something that we may talk, somebody may be talking about that tomorrow, but in the future, we definitely will be talking about energy storage and then different approaches to even using that storage for generating electricity using kind of gravity and all those systems where there's, anyway, I won't go into that. But so Eugenia, if you're online, would you like to say a few words?
Yes, just to say thank you to everyone for these super interesting talks. I think everyone is pretty happy, and everyone, the main mission of this workshop was to go away with some new knowledge. And also the good thing is, like, we are providing the presentations and the recordings, and it's something that you can go back if you were not able to attend to the full workshop. And yes, thank you for everyone, and thank you to you, Susan, for your great organization.
Thank you. And thanks everyone for your patience as we battled the gremlins, but at the end I thought it worked out pretty well. and I feel like you would be a good pitcher with all the signals. And I was thinking, anyway, so thank you, Eugenia. We really appreciate everything that you've done to make this happen, and want to welcome everyone to attend tomorrow at the same time, kickoff. And if you scroll through the chat, you'll see I put a link if you haven't registered for tomorrow yet. And I just put it again in the chat. So if you haven't registered yet, there's your opportunity. And thank you again. So I want to thank Eric and Kellen and John for presenting today. And thank you, Eugenia, for being our fearless leader. And we'll see everybody tomorrow.
Thank you. Bye.
Goodbye.